Hi, folks. I am Wang Belao, 说半岛. Today, I would like to continue my saga on the packaging process technology about die stitching, its yield and cost, and die size and reticles, and pattern walls associated with packaging. And three companies I like to mention the Apple, NVIDIA, and TSMC. And I would like to finalize with EUV versus the Canon Nano imprint lithography. And this all because all my analysis eventually goes to lay the foundation about how to do yield analysis. That's my main purpose of this talk. As usual, I always like to start my talk with some kind of icebreaker because my talk is not about giving you a simple technical details. I also like to inspire readers to know more about the development of science, and that is my major theme. And today I would like to mention this because it relates to our topic and it's quite interesting. It's the ancient book of wisdom at the heart of every computer, I Ching, right? I Ching, Chinese 25 the 2,500 years or more, there's a binary code used in the I Ching to predict future by the people, Chinese people then. It turns out the system developed by I Ching, okay, the binary code developed by I Ching, is actually fundamental of digital technology. Right? That's what's being used a lot. But who connect these two dots together, right? Well, we all know him, right? Leibniz. Oh, the Gottfried Wilhelm Leibniz, the greatest mathematician ever. We don't know that he invented the calculus, right? Same time as the Newton. Newton, I think they both fight. Who, the true inventor of calculus system, both have their own merit. But at the end of the day, who used the symbol, calculus symbol a lot? Of course, Leibniz system is the most clean one, and I'm using it all the time. And I think he deserves the credit as a true inventor of calculus. And it turns out he loved Chinese. Chinese culture in his time. He started to, read about Chinese language, technology, even as early as in his 20s. He's been infatuated by it. And his friend, one of the books says that there's a friend that male name that went to China and brought back a book of I Ching, especially this photograph, something related to his photograph. It's called Fuxi 64 sexogram. And he looked at these and he immediately sees, wow, that is the system he has been developing. He has been developing his binary code and it's being meshed very well with each yin and yang. Yin and yang is the broken and unbroken. The broken line is yin, means female. The yang is unbroken line. I think that's very obvious line. I mean, the yin, the female, is a broken line. Use your imagination, my friend. You could clearly see that very easily, right? And yang is the male, it's an unbroken line, one solid line. That's very obvious as well. If you cannot fathom that, I think you got a problem, right? And he perfected his binary system by looking at this 64 sexagram from this I Ching. We call Fuxi. Fuxi is a name, well, it's a mythological figure that Chinese coming from. They pretty much he symbol a snake. Okay. Anyway, yeah, they say that he's one created Chinese with his sister, a Nuwa. All right, they eventually form Chinese populations. And then he invented this system, I Ching, in a way to predict the future, when you're going to grow the crop, right? By looking at the moon and the sun, and then using his system, the farmer will know when to plant and harvest the crop accordingly. And that's the beauty of it. Okay. And Leibniz, according to his people wrote a memoir about him, said that he perfected his binary system by looking at this and studied this. And this, of course, his binary system is the modern computing, the one we are having right now, our computing technology based upon that is magic. Well, Leibniz loved I Ching us. We know it. I'm too. I'm too. I find out that I gave a lecture about the DOE design experiments in my other videos. You could find from here. Then I find out that I Ching also match well with the DOE with 2x2 and 3x2. You can look 2x2, two factor. Right? Statistics that we know is try to predict something. Same thing. They're using sample data and try to predict something in the future. And you look at that, for example, the plus here, meaning that you are changing you have a different trial. At this second trial, for example, you are changing something, make it more positive in one direction, and then two positive is you call this is the sun, two solid line, and then one positive, one minus. So you want to decrease your vector level on lower, right? And that symbolically is one sun and one moon. You can see here, one straight line, one broken line. And then for all negative, obviously they are all two moons, right? Two broken lines. So, etc., etc. For 3x2, you see the same thing. Here, see that? One solid line and two broken line is a trial of the first trial with A plus, B minus, B, C minus. And the third trial is plus, plus, plus. Obviously, is the complete male solid line, solid line, solid line. That's called qian. And complete broken line, that is called kun. And that's in Chinese means female. And this king, obviously. Okay, so you can see that the whole 3x2, 2x2 system can be easily explained by I Ching as well. Well, that's my finding, all right? I try to copycat Leibniz, all right? I'm not as great as him, but I try to copycat. But what's that got to do with die stitching? Well, I find out, well, you be the judge of it. Die stitching is, to me, two broken lines try to connect, try to dot, connect to each other. One die is yang, and you try to put two die together, connected. This is a packaging level, stitching two good known die together with some kind of interconnects, and that, to me, is some kind of an ink, right? And these, as we know it, packaging is a new building block of the future of computation technology. The scaling, as we know it, is going to be on one single die, probably reaching an end soon. And then the die stitching is the next step, right? That will keep the Moore's law alive. And I'll explain later what this means in terms of yield. So the yield, the interconnects here are the critical area for the yield. What do I mean by critical area? Well, we'll explain that later. All right. Now let's back on ours. Our topic is die stitching versus yield and cost, die sizes, reticle, pattern walls, especially pattern walls. I like to start with a summary of TSMC pattern walls. Of course, they are the big winner. You can see from the right-hand graph here that the portfolio size trend of the fine pitch packaging is what we try to focus on. Very fine pitch. And that's where the AI chips are done on. All right. You can see that They are far ahead with these small guys, and this one big giant here. And you can look the number for the advanced packaging. Okay, the total advanced packaging as August of last year has been reported is about 3,000. I think it's more, obviously more now. And then the Samsung about 2,400, about 500 less. And Intel far behind. And these foundries are, well, especially TSMC and Samsung encourage their engineer to come up with many patents. Intel, on the other hand, um, is not there. They are very careful, I would say. They are not that proactive. And you can see that their packaging is not as many as this guy, probably because they are not involving with a lot of customers as well. See, TSMC involved their process with customer directly. And then with so many brain working together, it's easy that you could generate patterns, right? When you see a new problem from a customer and you want to solve it, boom, that's a pattern, right? And then TSMC have worked with most of the customers, fabulous customers like Apple, Nvidia, Qualcomm, blah blah blah, and those people work together with sense with TSMC. Obviously, they have been they have their own unique problem that need to be solved, and TSMC is more than happy to solve it for them. And together, you can see that, of course, it generates patterns. You cannot generate patterns from nowhere because if you don't see a problem, you don't know how to solve them. And from the solving a problem, you find a niche, an idea that works, and boom, that's a pattern. And fabless customers take these patterns and IP's portfolio very seriously because they can see that, well, if you work with a foundry, assuming they charge the same price, of course, you want to go to the biggest guy because you have the more leverage of their patent portfolio or their IP portfolio. Then that it means that your yield will be higher. And then, so the other guy has no choice but playing some price war. So I'm going to give you cheaper price, right? 20% off, 50% off, whatever. Try to attract your customer. And and that's what Samsung been doing. And TSMC, I mean, Intel, they don't want to cut their price because they're very expensive already. And cut the price will hurt their benefit. But to be frank, it's not going to be easy. Okay. So you can see that TSMC leads in packaging patents. But what about the future? Is one die computing dying because of size limit? You look at the graph, the chip area wall. There's a wall here, 858 millimeters squared. That is a wall. That is how big a chip, a die can have by maximum. Because that's related to the maximum exposure area. It's 26 millimeter by 33 millimeter. All right. Later, we're going to see how it's actually doing that, how it's been done. All right. In a more graphical manner. I'll show it to you. And then you see the light go through the mask and condense it and coming down. And then see that the mask is, much larger than the field. This field is only about 26 by 33, millimeter. It's less than, it's just far less than 1 centimeter in either direction, right? And then this mass is huge. I mean, the lens is huge, all right? So keep that in mind. But at the end of the day, that's how big a field you can have. In a current 6-inch mask, this mask is only 6-inch square. Okay, that's how big your mask can be. So I'm going to make a bigger mask? No, you cannot. All right, I will explain later why you cannot in this talk or other talk. So if the computing power is transistor density times chip area, and this is fixed, you can't do anything. So only thing you could do is change transistor density. But you look at the trend, it's kind of saturating, isn't it? It's saturating. So that means that computing power will be limited by this curve if you don't do something else, right? But let's look at one company, recent company, Cerebras. Cerebras said, no, 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 I don't think so. So my idea is that I'm going to use my special technology called wafer scale engineering, WSE. I'm going to have one super die, supersized die, bigger than, McDonald's supersized the chip. And it has 46,000 millimeters square. The reticle limit, the die size limit is 558, as we explained earlier here. Chip wall is 558, but I'm making 46,000 millimeters square. Well, how's that possible? And I have only one die on one 12-inch wafer. Well, how's that possible? I thought, the textbook told me that yield is lower. You have a larger die. The larger the die, the lower the yield. Yeah, I have quite a few the video explaining that, and I will go through detail later in my talk as well. So how's that work? How's that work? That will be our discussion later. Okay. And you can see that if you compare the service, I think the key is here. The core area is super small. Yeah, 900,000 small dies, okay, connect together. Okay? And that we need to keep that in mind. And the other one is usually a big die as well. The area, not a die area, but the overall, at the end of the day, package area. Okay, the dojo, and then and this is a big one. And later, currently, we'll go through later the NVIDIA H100 is pushing limit to 810 millimeters square. All right, and how about AMD MI300X? Now, how do they do it? This die is pretty large. Okay, we'll go through that detail later. So my take-home message is that the die stitching, it seemed to me the future, even though Cerebras say the other way, the other way around. But let's keep that in mind for now. But die size yield still matters. It doesn't mean that if a die size, if a die stitching, then your die size and yield will not matter. Well, still matters. I'll show you how. Okay. So let's look at the Apple. Apple M1 Ultra is 2 M1 Max, non-good die, KGD, non-good die, stitched together, non-good die. I use this terminology a lot. Please keep it in mind. It's stitched 2 M1 together. And the connection itself is about 10,000 die connections. That's why its bandwidth is pretty high, a couple of terabits per second. And you look at the picture, it's like this, all right? It's two, and they connected together. All right? It's two M1. They must be M1 Ultra, okay? And then, wow, you see that looks similar, except the size are different. Well, that's the beauty of Apple chip. Apple chip mask, they could use the same mask or similar mask for all their products. For the iPhone 810, 811, 814 now, 815 in the future, they're using one half of MX system, MX chipset. And then this iPad using M1 chip or something similar, right? And then you want a higher end Pro, and then you got M1 Ultra. You got M1 Ultra. And Ultra is a stitching of M1. So imagine you have a mask. You don't need to have multiple mask set for multiple products. You have one mask set for all three products. Just maybe some product it requires some tweak. Okay, cut down some layer, make it less cumbersome, but the mother set is there. And all you need to do is change a little bit something. That makes the overall mask and chip design and print this kind of very easy, and it saves a lot of money. Why they can do that, right? The reason they can do that is they profit from the computer as a whole. And Intel and AMD profit, they don't only do one CPU, right? They cannot do the whole computer system. In this way that Apple can do whatever they want. They don't care about their own product. They only care about their own product. They don't need to care about other people's product. So they don't need to compromise. So they are pretty vertical integrated, right? And the and Intel AMD cannot do that. They cannot just copycat Apple's strategy because Apple have a huge captive market. They design their own chip, build their own chip, their own computer. So the MX are vertically integrated. And Intel and AMD sell a wide range of processors. Indeed, they need a flexible product and design to support multiple market, multiple. You have Dell, you have you have Asus, all these HP, different laptop, different phones. You have meet them designed specifically. You have to tweak it, make it more general. So that one you will lose a lot of flexibility. Okay, and so this is a high level message like to share with you about my understanding of Apple, AMD, uh, and Intel. And then this come back to what got to do with us in terms of the topic, die stitching. The die stitching to me, there are two die stitchings. I tell two cities. One is called intra die. One is called inter die. The intra die, the intra die is stitched fields inside scanner. You stitch field. You're not stitching. You're stitching dies. Here, usually you think of die stitching. You put two die together. That's at the package level. That's one of the more focus of this talk. But initially, let's focus on our discussion on the intra die, which is you stitch two lithography field inside a scanner, and you forming one big die. All right, and that's before you have one big good non-die, non-good dies. Okay, so let's go ahead. Part one is intra-die stitching inside scanner with two masks. That's roughly what we meant here. It's called double exposure lithography. It's a little bit different from the high-end lithography. It's an old terminology. It's double exposure on the same area, right? Well, a first exposure and a second exposure, okay? And then with two masks, of course, there's two masks. And then you take the wafer out, and then you develop your edge, and then you got your pattern, the final pattern. And this is different from the double patterning lithography, DPL. DPL is that you expose the same area, but you take the wafer out and then do some work, and you come back again to second exposure, right? And that's what you do. So, and that's what we know as the quadruple patterning, even more than this, like 4 times. Okay, not just double, yeah, quadruple patterning. But that's not what we focus today. We're talking about in the same chamber with stitching the field. Give you a perfect example. The phase shift mask. The phase shift mask is formed by this patterning with very different features, right? The facing photomask and you have trim photomask. Some are very large, some are very small. Okay, the feature sizes are very different. Okay, and then you have to do some crazy work, and then that's why eventually you got some here, right? So very thin and reasonably large features. You do this work because the lithography you're going to perform require these unique patterns. And then people done that with a sequential expose on the same region of the wafer to improve resolution. That's this technology being invented that way. It's called double exposure lithography. Okay, and so people done that. So what's the big deal, right? Intra-die, TSMC did that. Everybody doing that in part of the process flow. So intra-die stitching, the defects. See, we're talking about yield, right? So the major thing I'm concerned is about defect. It seemed to me that people already work on it for a long time, then the defect is not an issue. The pinching, bulging at all, they could, that's been solved. The edge, especially the pattern gap overlap, it usually has some problem. But this problem has been dealt with a long time ago. You look at the paper, this is 1987, 1988. People know that. It means that uh, has been solved, right? TSMC never complained that their DL doesn't work. They will hit their yield. Never mention that because that problem has been solved. It's not worth mentioning. And then so it's the illumination issue. Well, you overlap, you play your illumination scan, you can optimize it. Then the overlap, you obviously can get the same dose. So you have some leverage, some toolbox in the illumination system, in the scan system that you could play to get rid of this double exposure problem, right? Just a high level, okay? Then this picture change. The introduced teaching gets really, really complicated when we move into EUV era. It's different. Why is different? What's the big deal? Well, because the wavelengths you use, the wavelengths are so small, and then the reciprocal of that is your energy, pretty much. So meaning that the photon energy is very, very high. It's ultraviolet, right? EUV extreme ultraviolet. And this meaning that it's difficult for the light to go through something. Because when you go through something, say a piece of glass lens, when you try to go through that, the regular lens, it will be absorbed and the glass pretty much gonna get heat out and explode quickly. So you cannot let that happen. You will not let that happen. So instead of using a regular lens, as we see here, later we're gonna go to more detail. See, imagine if it's EUV going through here, this lens is going to explode. You can absorb the 13.5 nanometer wavelength and get heat up, and this lens made of glass, obviously, is going to heat up and explode, right? So, no, you cannot use that. EUV cannot use that, okay? So what do? UV use something else, okay? And the U technology will use mirrors. We'll go through that later in this talk or other talk. But so what we're going to use it then? Why struggle to use that? And then what's benefit? In a high level, if you look at this Intel 4 nanometer EUV process flow, if you're using Intel 7, which does not have EUV, and as the benchmark, and then if with the without the EUV, you had to add a 20%. Okay, because the double pattern. Remember I mentioned here, you in this double patterning lithography, you have to expose and remove on exposure, and you do develop, and you put a resist again and put it back. Well, every step gonna hurt you because when you do this step, it will create particles, and then you have some other problem come out, but you don't know yet, right? That's a big problem. So, but sometimes you have to do that because your pattern is so small, and the current lithography tool like EUV cannot do that. So you have to use multiple patterning. But with EUV, you could use one mask to do it all, right? So, and that will reduce the process flow. See that? More than 20%. That's why Intel in the total mask account. Total mask account is the number of masks going through a process flow. Maybe 80, 50 to 80, depends on technology node, right? And then and you can see that with EUV, you could cut down this off, right? You could cut down at least 20%, 25% of mask used in that process flow. And that, meaning that could potentially more yield, right? But EUV is very expensive. Oh yeah, it is very expensive. So this means that we are spending more money to save money. But why we save money? I thought we're spending all the EUV costs, 100 million, 200 million, all this crazy amount of money, most expensive money machine in the world. And you're saying saving money? Yes, that's exactly right. You look at because the process flow is saved. So the wafer stay in the fab will be at a shorter time, and you have faster turnaround. Okay, from your product from your die to market, your product to market is shorter. All these means money, and then the yield is higher. That's money too. Without EUV, you save some money for not buying it, but you pay the price for lower yield. Okay, you cannot do that. All right, so at the end of the day, you have to master EUV. Otherwise, you cannot go. Okay, and so people, what are EUV, right? The EUV has a lot of intro die stitching. We stitch two together. In its early days, 1917, TSMC already doing that. So you look at the patterns, it's very obvious. So this is the one wafer. They say the first exposure and the second exposure on the photoresist. Okay, the photoresist is the same. They did not wash it. Okay, careful. Let's just come back again. It's like this. All right. The resist here. And here, double patterning, you wash it. You clean your resist and put a new resist on. Here, you own the same resist, but on a separate region of the same die. That's a major difference. So the first part and then the second part on the same resist. This is the dark master resist. All right. And there's an overlap area. But you look at the classic Dell, it's different. Classic Dell, the double exposure is you are done on the same mask, same field, but different exposure, right? It's not separate. This is the same die area, same die area. Okay, so that's a major difference, and that's a challenge. That's the word challenges because the overlap become very critical. It's very difficult to align perfectly. And in 23 last year, they have this similar pattern. They are now say, oh, see, they have those fancy alignment mark. You need to align them beautifully, perfectly, and how to do it properly. Of course, they won't sell that. They won't tell you that in their pattern in such a detail, but you can sense it. Right? They have a lot of unique features in their pattern that so as their alignment, okay, alignment CDs had to be perfect. So that to reduce the 3 sigma CDs in terms of alignment. So the overlap has to be done properly. Okay, so all these patterns, there must be 100 of them. I give you a few examples. They keep working on it every year to generate pattern to protect themselves. Okay. So as I mentioned, intra-die stitching is not new. So what is the problem? The problem is that it's done on a separate region. Well, separate region, what's the big deal? You could, as you know, the overlap region, you can optimize it. But the challenge is this. You've done everything inside a vacuum with 1 nanometer accuracy with throughput of 200 wafer per hour. Wow. You have to do fast and very accurate nanometer accuracy. So my takeaway is that you bet the Maxwell demon out of a Pandora box to get you. Everything you work on extreme dimension with extreme acceleration, extreme the acceleration, then the handling of that is very challenging. Right? Let's look at what actually happened. Right? This is a field. The purple one is a field. And what is moving? The mask is moving 4x. And then the wafer stage is also moving. Everybody's moving at the same time, right? That's amazing, right? So this one, that's what I meant to see that. Oh, it's slower now. You can see that. Yeah, that's how they eventually print a die. Okay, each die here. The slit That's the size limit. Okay, so you see that? Oh, see, that's how they print. Sometimes they print one die, sometimes print more than one die. But anyway, your mask stage has to move very fast because at the end of the day, you need to do everything here. Right? See that? You're scanning. You have to do everything here. 200, couple hundred. Oh, this page is 220 wafer per hour. Oh my God, how fast it's moving! And then you cannot miss anything. You have to have a nanometer accuracy. Otherwise, you print it wrong, and you're doomed. For the uh, for the low NA, currently the low NA 0.33 numerical aperture NA1, you have full field. This is 33 by 26. It's 26, 33 full field scan. But for a high NA, you could only have half field scan. Sorry, you print half field. And that's where the challenge is. Okay, so let's leave that cartoon aside and look at more technical detail. The regular versus high NA UV field. The regular is your this is a 0.33, it's 0.5. This half field only generated by high NA. Okay, high NA. This is slit direction, and this is how it moves around. And look at back again. All right, see the slit, and then this scanner moving. So they are doing this way. This purple slip is this one, the yellow one here. Okay, and it's scanned. That's the wafer's holding stage is moving. All right, and they are accelerating and then deaccelerating. Remember, there's acceleration and deaccelerations. And then so the field size, this is classical full field or low NA and DUV. They are all using a full 558 millimeters square. But half field is only you can do same 26, but scan only halfway. But why can only scan halfway? All right, what's going on? So that's what be in my other talk, and that's a UV I'll talk about. But just keep that in mind. It can only do half. But what makes things worse is this: the multi-E beam. All right, that we have to the mask here. The mask stage, the mask here, this one, you have to generate a mask. How do you generate a mask? Well, you use called multi-E-beam for mask writing. There are only two companies in the world can do that. Well, IMS and Nuclear. I have a talk. Well, we'll discuss these two companies. A multi-E-beam, all right, and this is what make uh, the pixel base such a powerful tool to generate crazy patterns. What I mean is that this is a crazy pattern. See, if you want to print a small hole on your wafer, what will my mask look like? Well, my mask, which is about, here is 4x, something like that. And that means that I'm going to make it the whole 4x larger. This is suppose that's what you want. Can I just do a 4x larger hole on my mask? Well, it turns out you cannot. It's not enough. You had a lot of this crazy assist, this curve one alongside. But why is that? Because the light you use is 13.5 nanometer. And this hole may be 5 nanometer. So fundamentally, the light cannot do that. It cannot have the resolution to do so. Because the wavelength is already 13.5. And you printing a hole similar to that size or a little bit smaller than that size, you cannot print. So how do you do? Well, you fool it by placing a lot of this kind of a features, so you bend the light around it, and with a hole opening, then at the end you could able to get a small hole here. Okay, and this technique right now is called copper litho, and D2S with the AI assistant, because to do this shape, you need to use a huge computing power. Sometimes I remember one of my colleagues told me that when he submitted for the mass writing to the usually supercomputer, whenever he submitted a job, it take a week to come back. I told him that you got an easy job. Wow, you submit a job and then you go home and rest for 1 week. I just laughed, right? But that's how it works. So right now, no, 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 no. Such a small feature, such high computing power required with the use AI, right? And that's where the copper litho come in. Copper litho is NVIDIA with TSMC and D2S. D2S, and they have their own idea, right? So this is what they meant. The previous one, the curvilinear ILT. Okay, this one, curvilinear ILT is the technique we're talking about. That they what they try to do is to have the shape. They make shape any way they want it, pretty much, by through the computation work they've done. So they could easily get their different shape to work. So what's the purpose of having this shape then? You fool the light by creating these features. The main benefit is this: you have increased your depth of focus almost 2x. That's the beauty of it, and you can print things easier. So that's fundamental. D2S working with Micron on this topic. Even though funny thing is that EUV does not really use in DRAM world. Right? Only a very few later using it, but they still work on it, right? Yeah. See, this company pretty much is a new player, right? It's a Japanese company um, that initially come with a VSP, various speed beam, and now they come on multiple beam. This used to be one beam. You rest around, all right? But the new mask, the new e-beam is multi-beam. You're writing on the mask with a multiple electron beam, up to about a quarter of a million beams riding on the mass at the same time. Imagine, how do you handle that? A quarter of a million beams. This is what I mean. Usually, this is what I meant earlier. You're using a VSP, one beam. You write carefully. Yeah, you could do it, but it takes forever. And you want to write this, that's going to take you a long time. But if you use a multiple beam, you have multiple beam coming in, right? I told you that. I just mentioned you have a almost quarter of a million or more electron beam is available for you to write if you can control it. So at the end of the day, you could have pretty much, because you have quarter of a million beam, you have more than quarter of a million electron beam to write on the mask to create your mask you want, and you of course, and you could do anything you want, any shape. Right? That's key. Print any shape at the same time, and then there's no runtime penalty. you probably finish in a couple hours. That's it. 1 hour, couple hours, you're done. If you do USB, maybe take you a week. That's a major difference, right? And then this curvilinear ILT can really write this fancy strange curve that's computed by your copper litho or T2S, this huge computing power, AI assisted computation come up with these features that bend the light the way you want it to, so as this big hole can produce a clean small hole here. And this just disappear, right? Here you don't have here. All this you don't see that on the wafer because the light going through here through your calculation disappeared. All right, that's the beauty of it. Okay. All right, that's enough of intra-die stitching. Let's focus on the inter-die stitching at the package level. Okay. And you can see that this is where the Apple, AMD, Nvidia focus on. All right, they don't care about intra-die stitching. They don't care. Right, that's TSMC's job. And they're not involved in that. Just print. And then I don't care whether you use INA or not. Right. You solve that problem for me. And then the Apple inter-die, you look at the series pattern they have, the 2020, right? They have this stack, all right, how you die preparation, how you place the die, and you connect them, and you figure out something, and so as that they don't have gap. So all these are done um, uh, in these patterns, in organic material gap. This is kind of an old pattern, like old patterns. Okay. And then a new one come out. You look at the new one. This is a new one. Good known die one, good known die n, and put it together. All right. And then make it, and then they stack on the one wafer, and then you package it. So of course they don't give you too much detail, but this is obviously a part of the a CoWoS system. So they put multiple die on one wafer. This actually the chip on wafer process technology, stacking technology for the TSMC 3D fabric. One of them. They're multiple. They're wafer on wafer, even die chip on chip, die on die. They're working on it, right? That's very powerful, right? And here, this is a chip packaging, is advanced packaging. Oh, they're running on name to name this, okay? And the point is that here I would like to focus on pretty much the interposer here. This info is a lower tech, not too, it's not related to the die stitching. All these are more related to die stitching. It's a silicone interposer, RDO interposer, probably organic, and then the other type of mixture. Okay, so all these are critical to your chip level. I mean, package level in terms of AI chip. Okay, and Apple continue to do that. This is a recent one. Wow, they have even more fancier patterns. They want to make sure the connection is the way they want it, right? I mean, then they will share with TSMC, and then they would work together, learn from each other, and then implement the process. Yeah, that's how M1. This is, this series of pattern is what eventually come up with a product. The product is is this, right? The M1 Ultra that come from these patterns. Otherwise, people can copycat it and they'll be in trouble, right? So they have to protect their patents this way. Okay, continuing come out, continuing come out, and so this is last year I saw, and probably more, probably more. And you look at the overall package that TSMC offer, they're dominating this world, right? And everybody try to catch up. And they have multiple technology available for the customer to use. And they are, I will talk about what is the yield number of their technology. And you look at the NVIDIA H100, it's also a big baby, right? They have to use the so-called MCM, multiple chip module. They put everything together on a big piece. Give you an example. The H100 is Cole's 1-800, this one, GH100 die, graphical GPU die, with 6 memory in an MCM package. So eventually is one big the GPU with 6 memory package. Okay. Here, one big. Okay. And then how big a die? Oh, 814. And then the A100 even bigger. Okay. Tesla one is A15, the same size, pretty much. Okay, this is a new version. The Tesla P100 is only 600, but it's still big die, by the way. These are big. The bigger die, the biggest die you can make is 858. In reality, you cannot make die that big, right? You have to give some area for other things to connect you to. And here using the M4, okay, M4. And so you can see that it's a call it Goliath. Yeah, bear with me on that. And then you look at their pattern. The pattern's face-to-face 3D. Wow, I think it's a fusion GPU. They want to do that. I don't want to stitch it. They stitch it on top of each other. All right, they are more advanced in a way that if you look at the apples, right? Apple is this stitched side by side, right? Top and bottom side by side. And NVIDIA said, oops, I think I got a better idea. I want to stitch the top and bottom so I can save more area, right? And Apple don't care about area. They own the chip. They could modify their laptop that way or their iPhone that way. They could okay with that. But here, NVIDIA, no, I have a better way this way. So is this new? But I look at this pattern, it's strange. This extra long TSVs. And it's kind of scary. This is super long, kind of scary to me. It's not easy to make a very long TSVs. It's good for a pattern, but rarely can you do it. I don't know. Okay, we'll see. People can play magics. And what about AMD? I call H100 a Goliath. And then, of course, you would think about David, right? David against Goliath, this cartoon. A little guy beats the big guy. AMD die are small, right? And what I meant small is that small compared with H100 because its die is 1,000. It's not so small. But what I meant small is that it composed of 8 small dies with each die XCD is the 115 millimeter square. And you had 8 of them stitched together in a package. All right. So the total size of that package in terms of AMD MI 300X is about 1,000 millimeter square. Okay. There's 8 of them, right? And they claim it's better than TH100. That's the bottom line. Right? So I would say that. And you love to play David's against Goliath game. They did this when against Intel, right? AMD's chip and the same technology node is smaller than Intel chip and that node in the old days. And the only problem so means that their design is better. The only problem with AMD is that they cannot make it enough. The yield is low. So they throw that problem to TSMC, solve that yield problem, and can produce tons of a little bit better CPUs and GPUs versus Intel than they want. Right, that's what happened. Now, right, AMD take over pretty much Intel in terms of the size, and I think they are doing the same thing for NVIDIA. NVIDIA is humongous, H100 and B100. B100 is 2x of H100, even bigger through die stitching. Okay, so AMD is there's a chiplet technology called Active Bridge. Right, same thing. They want to connect everything, right? And then they have this L3 cache. All right, they try to optimize the interconnect between chiplets. Okay, they call it infinity fabric. All right, is what they call it. And M1, MI 300, not M1, MI 300X. Actually, it's pretty marvel. Right, it's a 100 piece of silicon. Okay, stuck together, all sitting on top of record-breaking 3.x reticle silicon interposer. And this is currently TSMC can offer. They're moving a bigger one now. Right. By the way, TSMC is not stopping at 3.5x. They're aiming for 6x, and they are doubling the capacity this year. Let's look at their one of their announcement. This is what they announced last year. The course update. You see that this is the old. We do 2x of reticle. One reticle is 858 millimeter. 2x is 1600. And then 2023, see this is a package AMD, close to AMD MI 300X, right? You have 12 high band memory, 4x, 4 chip. Wow. AMD's MI is 8. Okay. And then eventually they say they're going to do 6x. 5,000 millimeter. Okay, that's the goal. And they deliver 3.5x high volume manufacturing, meaning that they already done in large quantity and then deliver that right to AMD. So the technology is mature enough. So what they did what they said, pretty much. That's what I meant. There's no lag behind in carrying out what they say, in fulfilling their destiny per se. Yeah. And we look at the AMD and Nvidia die, size and stitching or not. This table I prepared for you. These are MD3i, MI300X. It's 5 nanometer. Okay, intra-die stitching and package. Total 153 billion transistors. Is stitching 8 die together. Total 920. And then you need stitching area, right? So the total area is about 1,000 millimeter square. NVIDIA, on the other hand, is 814. Total transistors more. Less. This is 153, this is 80. Okay, so that's the reason MI 300 is claimed to be better in performance than the slightly older generation of H100. But the node that I'm putting on different. TSMC 4 nanometer node versus 5 nanometer node. Because AMD wants to save money, the cheaper one. And then 4 nanometer node, probably capacity being bought up by NVIDIA. But if you look at the recent one, B100, whoops, 1600 millimeter, 208 billion transistor. It's 2x of H100. H100 is 80, so 2x is 160. But they claim it's 208 billion. And he says that reduce cost and energy by 25x. So this is new NVIDIA B100. And this one, I think, beat MI 300X. It beat H100. But what about this? I don't know. We'll see. But that's good, right? As a customer, I like to see them beat each other. Beautiful. No problem with that. Okay. And then if you look at the cache, the previous generation, the Ryzen 7, they already have this beautiful interconnect. And the one thing I'd like you to notice this graph is the direct copper to copper bond. This is the first time that I think TSMC offered to customers. Copper to copper bond, HBI, hybrid bond interconnect, right? This is a technology that everybody tried to master. Without that, you cannot go to finer pitch on the package, say a couple micron. You cannot do that. You have 10, 20 micron, then you do regular bond. But when you go down to sub 10, you got a problem. You need copper. But copper bond is fantastically difficult. And currently, it seems that TSMC is the only one that could do it with a high yield. with the help of the other guys, right? There's EVG, there's Betsy. All these companies are pretty good at it. Okay, so and that's how my Intel, uh, I mean TSMC can be number one in the world. They have this ecosystem of supplier working with them together to make their process work. Even though these companies work with the other customers as well, but for given reasons, various reasons, they did a better job when they worked with TSMC without money. Okay. So if you look at the roadmap of packaging, you can see all these different technology. Okay, CoWoS is Intel, Cerebras, and this SQ, Samsung, all right, and more. And this is TSMC again, SOLC, all right. So they jump from here to here, and then this Intel is uh, Samsung, but Samsung is far behind, a couple of years behind, I think. Uh, then then TSMC. This can reflect on the customers. Right? You just go check how many customers they have. Customers are the best predictor whether the technology is mature or not, right? That's real money. Everybody can put a PowerPoint, but when you put the money to your mouth, you know who's speak the truth. Okay. And packaging technology for semiconductor has evolved quickly since 2000. This McKinsey the pictures kind of do history quite nicely. On the wire bonding, just wire them, and then you put something in between, and then the wafer level 2.5 means what? They have connect each other and then stack. You connect as 2D, right? Connect through TSV, and then you stack them, so 2.5D. And then the 3D stacking means everything stacked up. This is still ongoing, not perfect yet, right? Because it turns out it's quite hard. Imagine, because the reason it's hard, I have I present this analysis in the other talk. Basically, it's this: you want to put the die on top, on beside, beneath HBM, a memory, you're gonna kill yourself because die gets so hot, right? And the memory don't like that hot. They can tolerate some heat, but too much heat, you're in trouble. So, so that's why when you're stacking together, how you stack them is very, very critical. How do you cool it? It's very, very critical. So the idea of the PowerPoint is very easy, but this one has never been done properly. I mean, in a high volume manufacturing per se. It's done in a laboratory, but in the real world, you cannot do that for now. For example, the NVIDIA, what's the output power? It's 1,000 watts. Oh my God, 1,000 watts, right? So you can see how high it is. And then the cooling become a problem. So I have another talk about how you cool the wafers when you package it. So the CoWoS, you go a little bit deeper. It's 2.5, right? You connect here, all right, and then you stack up to 2.5. This is 2 and 0.5. You don't do everything together. The logic here, you don't want to stack logic to logic, right? Then you has to be super hard, and you're gonna burn the damn thing. And then here, while you play the game of RDL, redistribution layer, you connect how you connect these together. Say so you have many things you could do, right? The inside this interposer, and then the inside interposer, then you do a lot of say silicone. That will be high end, very rigid, strong, mechanical strong, very good, but gonna go high end cost, right? For your high computing, uh, the high performance computing need. So that's your POR. The glass, everybody want to do the glass now. The glass interposer is coming. Intel is doing it, and then everybody's doing it. And try to see because they have lower leakage and more rigid. You don't have a warping problem. So that I think now could be the future. We'll see. An organic one, of course, you put a glue there, you glue everything together. It's the cheapest cost, right? And that's again, the TSMC also have that in their portfolio. Okay, so all this, the RDO here, yeah, some of them are organic one. See, and that's what they are offering that a lot as well. And the technology obviously is mature. Okay. Yes. And then so okay, let's look at the yield. As I promised, I give you the yield. This only one yield number I saw, right? Has been early days. They say, well, their yield is 91 millimeters square is 85% a yield. But they achieved 100% yield with a larger area, 110. That does not make sense, isn't it? How can you have a higher yield for a larger package? So that's a question I'm going to ask, right? And then remember, you better have a package yield because you are using these non-good dyes. These good dyes is very expensive. I give you a cost of each dye later on. A couple hundred per dye, pretty much. 300, 600, you name it. And you put two together, that's like 1,000. And if you package it wrong, oops, then that package fail, and that's cost you $1,000. Whoa, that's not good, right? But compare with what happened in the process flow, you could stretch, TSMC stretch bay wafers before the forming the non-good die with low cost. It's just send more wafer coming in. They will do that. They always start more than you need. Right? They already comprehend the wafer scrap, the yield issues. So that's what we comprehend. And now look at it. M100, 300, and MI300 has 100 silicon dies. Right? If they have, as I mentioned here, it's incredible. The package 100 pieces of silicon stuck together. If any one of them fails, the whole package is gone. Imagine the cost, right? So it's kind of scary from the perspective. Okay. And so I'm going to start to analyze now. Well, okay, just compare AMD and Nvidia die yield and cost. All right, that's the final portion of my talk. I have another portion. Sorry. Let's go through. Before I give you more detail, I'd like to introduce two yield calculators. One is done by me. All right. I've used ITRS yield model to predict TSMC large H100 yield rate. And the other one from Kelly. Kelly had to come up with a die yield calculator. He put a number in. It's straightforward. Mine is more theoretical, but let's put two together. My model is not my model, it's ITRS model. Okay. He says that with a negative binomial, they will see that the yield should follow this curve. The yield probability should follow this curve. Okay. And it's called then the end result of the binomial is called negative binomial with the yield rate like this. A is your critical area, and the D0, D0 is your the defect density, and alpha is the parameter that lets you play with the game which one you believe. And alpha equal to 2 is the one recommended by the RTRS, right? So, there are many different models, but at the end of the day, this is a summary of various defect models, the pure Poisson, Murphy model, C's model, Boyce Einstein model, negative binomial model, which I use. All these predict, you see that die size versus defect yield rate, right? As the yield always lower for larger die size. Smaller the die, the higher the yield. And that's the reason big driver for chiplets. Make a chiplet small, the yield is higher by built-in. A larger die, lower yield. But how can this explain the Cerebras super die idea then? Okay, let's put it aside and look at the yield number. I want to know what is the D no number here, the defect density number. Okay, if you look at TSMC 7 and 5 nanometer yield rate, it's 0.1 defect per centimeter square. This is huge. I mean, this is hugely small. pretty bad, pretty good. I'm sorry, pretty good. Get my tongue tied. But and then 5 nanometer yield rate is better than 7 nanometer. You see that? Why is that? Why is seven? You know, it's usually when you start a new technology, your use should be worse. But seven is better than 10, and five is better than seven. Wow, amazing. And at the end of the day, they look the same. Right? I'm talking about initially. Initially, they all like zero point 0.1. Okay. When you run more than a year, the yield stabilized. The reason is that the number of EUV tool used. With one UV, you have 4 DUV savings. And when that saving means that more, so this saving is big. Okay, you save a lot of big UV use. 5 nanometer continuous trend. And this is why people want to go with EUV. But to make EUV work, as TSMC shown here, it's not easy too, because the same curve, I'm not sure is shown by Intel or Samsung data. I never seen any data they throw out with this defect and the defect number. Oh, I didn't see that. Maybe you could find it. I couldn't find it. Okay. So with that in mind, TSMC is better than textbook. That's what I try to say here. The textbook is here. The textbook is here. That's been used different models. Okay, I use these TSMC model. Okay, and then I use the negative binomial, and then I try to calculate. This is how I calculate. It's been reported that the TSMC yield done for the apple, about 1 by 1, it's 90%. Okay, or even higher. It's still 90%. Then the question is find yield rate versus die size. So let's calculate the defect density. All right. You could do that by using this number, immediately calculate defect density is 0.105. And this is how I know that number is good, because this is what happened here. Matched very well with the true data. So my model, D0 estimation is quite accurate. Now put the alpha equal to 2, then you can see that this is the actual yield I calculated with this negative binomial formula. Why I want to do that? Because I want to know this number, 8.1 centimeter square. All right, and that is the die size of H100. Right. Let's compare this data with Kelly. Kelly data, applying defect density of 0.1, right? This one. And then the 10 by 10 millimeter, I got 90.56. You just go to this website, all right? I listen to the website, and you just go to the website and input this number, defect density 0.1, and then the die size 10 by 10, everything leave it blank, all as was. Then you get the yield is 90.56. It's matching very well with mine at 90%, perfectly. Then let's look at the yield rate of H100. H100, I would say, is 25 by 32, right? The die size. That's an estimate, because I want to use a full field, right? I cannot say a square. I don't want to do square. It has to be 25 by, because the reticle size is 26 by 33. All right, so I use 25 by 32. Good estimate. So it's 800 millimeter. Then our yield is 48%, roughly 48%. And mine is what? Mine is roughly 50% here, roughly 50%. So very close. So with that, you can see that TSMC 800 centimeter yield is 1/2 of 1 centimeter yield. Here is 1 centimeter. Okay, about 90%. Okay, 1 centimeter. I'm sorry. Here, 1 centimeter. It's 90%. And then here is 50%. Close. It's close. Close to 1/2. Right. You could, that's a ballpark number. Okay. Then just use that and start to do some work. AMD MI300X versus NVIDIA H100. AMD has, you have 8 dies, right? Each die, the name of the die is called XCD. You have 8 of them. And then your die size is 110, 115. The corresponding yield using caddy is 89%. And you have 365 dies, good dies. 395 good dies. You divide by 8, so you could generate 49 MI300 non-good dies. And then NVIDIA, you do come up 47. This number from Kelly is matching my number closely. Okay. Does that mean that TSMC can produce AMD chip a lot cheaper? That's my first question. Actually, it's not. If you look at it, it depends on the reticle utilizations. If AMD die 100 and somehow, just hypothetically somehow, right, is not a perfect one because the area they use is only 115. They cannot, if they stack them together, they cannot use a full die, 858, even they stack them together, right? The area is 58 for you by using 115. So you stack 6 or 7. That's maximum you can do. So your utilization is not perfect. But there's the people who calculate that. In the worst case, that since you're not utilize the reticle 100%, then you spend more time inside a machine. But the wafer should scan more, right? To get the same amount of die, then that costs money. And the little money is the more expensive one. In one cases, the chiplet MCM package code can be like 2x of the regular non-lethal regular die that's used for die. So the overall cost is like 15%. I would say the worst case is 15%. And we look at the AMD, the TSMC cost numbers, right? See, the 5 nanometer 600 and 60,000, 16,000, and then the 3 nanometer 20,000. I use that number. Let's see, everybody using 5 nanometer, and then with a 15% markup to produce AMD chip. And TMC call for making AMD M1 300X, and is this 16,000 divided by 949 times 1.15. 49 because of this, okay, here. Because I could use this 395 divided by 8. So one wafer, I got like 49, right? And then the NVIDIA, the die is so large, my yield is low, I got only 27. I put that number in, then the cost for TSMC, according to my assumptions and estimate, will be 375. And then the S100 will be 590, roughly, give or take 10%. Right? Of course, packaging cost excluded. And that's the basic estimate. I use a simple yield model and then the reticle utilization model to give you that estimate. About 2x. See that the MI 300 is cheaper? Not exactly 2x, but 2x shy. Okay. Then the packaging level. Can I use the same formula, right? Any formula here? Well, it turns out yes and no. You can see use the same type of same formulation of the model, but the critical area you are not going to use the same because the die stitching, the particle, the die is perfect. That's how you get it. So there's no, so your area here should exclude the non-good die area and focus only on the interconnect area. And that's the reason why in this package, a larger total area get a better yield than the smaller package because this one has a more advanced, better a lower defect density, and a better interconnect technology. Okay, this is INFO and this is SOIS, and this is a more later technology, more mature. Okay, and they know how to handle this connection better. And here, not yet. Okay, so that means that the critical area here is not the die size, it's the interconnect size. You could think that way. And with that, you could look at the Cerebras super die. So what they claim is this. They say, my die, I have a lot of redundancy, built-in redundancy, right? If one failed, certain probability of one fail. Of course, you look at the defect density of TSMC, it's only 0.1 per centimeter square, okay? Which is one defect per 10 centimeters square. And then I have here a many small one, 900,000 one. It won't fail, but I have a redundancy building next door. So it's fine. So that's the idea. Okay. So only the one really hurt them is probably the interconnect. So with this idea of using small die, redundant die, building redundancy die is being used in the hard drive and memory business. In hard drive chip that they use is so small, and then they don't care about the dust particle in system. So these 100 particle, 1,000 particle, I don't care. I have 10,000 dies. Here is you have 900,000 dies. So with a particle, here the particle density, so you got a 10, say even 0.1 per centimeter square, and then for a size of 300 millimeter, you could probably of 10, 20, say 100. You don't care, right? You really don't care. So that's the reason that with the built-in redundancy. So this kind of indexing, I call it built-in in die. Okay, there's too many names, let's forget it. Right? So that's the idea behind Cerebras. They use redundancy, and when you, especially for memory guys, right? That's what they do all the time. They have redundancy circuit built into the memory because so repetitive. So they could do that. So the raw yield is always can be improved by the redundancy. When they do a fixing repair, the final yield can always be higher, much higher, could sometimes be much higher than the product yield, than the initial raw yield. Right. So that's the idea. Then of course it seems working from that idea, but how effective it is, I don't know. First of all, your baseline has to be clean. So for this reason, you go to TSMC to get that. Right. The baseline defect density is low, so you don't need that redundancy. You cannot redundancy every one of them, right? It doesn't work that way. Then you have only half a. So you redundancy every one of them, then it's not 900,000, it'd be 450. So you have to selectively do something, just like a memory guy doing. Okay. And then so that pretty much ends my yield talk. And let's go to the extra bonus Canon nano imprint. The question asked is that Canon the nano imprint disrupted to EUV technology. That's what for you gotta look at the data, see whether yes or nay. Right? EUV versus NIL. This is in the Japan, the Nikkei. I don't always like to read this Japan Chinese the publications. Very nice. Very a lot of information there. So they compare EUV with NIL. Right. I'll give you more detail here. EUV, you have the multiple lens and come on to the wafer. That's eventually what you do. And so you need to have all lens. Wow. Mask. Wow. And then here, no. See, this is a mask. And here, it's direct. You're right there. It's direct. And then the wafer hour right now, it's 80. And then in this table, it's talking about if you do 13, so equivalent nanometer. And if this worked, that's a miracle. You don't need fancy tool. Okay. And look at the flow. Let's look at the one typical flow. It's pretty much a direct writing without using mask. You don't need a mask. Okay. So it's just imprint technology. A prime droplet. Uh, I'm sorry, you didn't need a mask. You need a mask mold. I'll take that back. Okay, I correct that. This technology still use mask. Okay. They apply a mold called mask, but with a patent. The idea is just mask and then ultralight, develop it, and then remove it. Mechanical. It's very simple. Idea is very simple. And the thing that caught my eye is that it has no reticle limit. You don't care. You don't. There's no 858 millimeter square limit for NIL to work. That's not the concern. You could do ideally any size, right? But the only problem, I think the biggest problem is 4 nanometer overlay accuracy is not there. So this is not enough to compete with EUV. And on top of that, the defect is the number one concern. Okay. And then there's many different ideas. And this picture I want to share with you, the one thing is very important, how you remove it. So this is a mask, how you remove it, and how do you apply it. Suppose you have one particle sitting in here, and then you have to repeating using this mold back. And the particle sit there, if you don't clean it in a proper manner, then you're dead, right? So this problem is being the biggest problem that why this technology is not being practiced. But of course, people know that, right? What's the big deal? People know that, and said, and then the company Canon, who bought the company a long time ago, and then keep improving it. So they could say my placement error is much better now. So the three sigma, it go to used to be 2.74 and then 2.21 these days. So they are better. Or now the full field is 1.83. So they're better. I think that that placement of the mold to the wafer is can be controlled in a nice manner. But I don't see clearly how do you solve particle problem properly. So because in PowerPoint, right? All these. So I try to find the yield number for each process. Unfortunately, I, uh, I cannot have that. I don't have that. All right. I don't see if somebody report the yield number is it equivalent to a regular yield like 90% or is say in that sense like 100% or TSMC that kind of yield. I don't see that yet. But who's buying this machine? It's obvious is memory market because memory market has a lot of repeated patterns, right? And they so in this way, the repeated pattern is easy to handle. It's all vertical coming across each other. It's much easier. And then Samsung working on with Toshiba previously, the memory company previously, of course. And then Korea, SK Hynix, Samsung. I think they all think this could worth a try, but I don't know whether it's been HBM yet. I think the fundamental problem is that they are limited in terms of even they say I could fix my variability problem, the sigma problem, I could fix it the matching, the cross-match machine overlay that could matching the regular EUV technology, okay, by controlling many. But the part, what do you handle the how clean the mold is after you use it? Because the problem is that it's a direct contact. The direct contact kills you because you're touching something when you lift off. If you have some sticky things, then you got to put it on top of the next one. And imagine how fast they're moving. This we're talking about. This is 70 wafer per hour to 100 wafer per hour. You can have that speed. And I think that's a problem. We go quicker and quicker. I would say the Maxwell demon come out like catch it. And then they claim that the roadmap, they think there's a position here. All right, they could make it work. That's uh, the nano imprint lithography side here. My personally, not a big fan of that because it's going to be very challenging. They kind of late in the game as well. The only advantage they are a lot cheaper. They're not super cheap, but they're about 20% of UV machine. But you have to be 5 times better. So that one, I don't know, not yet there. Let's wait and see. I'm happy to see people work on new technology. This technology is invented by Chinese Americans, and then he had a company and he sorted it out. Uh, and then this has become part of the mainstream. That's pretty good. Okay, I'm amazed. So this keep that in mind. This could be disruptive. Right now, it's not. Okay. All right. Thank you very much. That's my talk.